and I mean, it's because we have a collaboration within IPIC on various things, and one thing would be that we are actually in need of a UV source. So that's the reason why we have this type of presentation. So first, UV light, what is that? I mean, that's energy or light that is to the higher energy than visible light. So UV radiation would be divided in UVA, UVB, UVC, and UV, vacuum ultraviolet. And typically light sources that have been used so far would be some type of lamps in that region. Low pressure mercury lamps is typically something that's used quite a bit, and it has an emission line at 254 nanometer, 183 approximately. So they are indicated here. Vacuum ultraviolet, it's called that because that radiation actually doesn't penetrate through the air because oxygen absorbs it and produces ozone. So ozone is something that protects us from UV radiation from the atmosphere or from the sun, basically. So that's the ozone layer that we are so dependent on, because that absorbs the ultraviolet light as well. But also it's produced if you use radiation shorter than 200 nanometers, basically, because then oxygen starts to absorb and divide itself, and then the free oxygen atom will react with the oxygen molecule, producing ozone. Ozone is something that you can smell close to a copying machine, for instance, because you're using mercury lamps there. So that's a little bit of this. And if we then look for semiconductor sources, so this I just took from your slide, Peter, from a presentation that you had previously. So just showing that, okay, this is the wavelength range here, and we are just trying to see that in that region, in the ultraviolet region here, it's actually a gap. You see this is a log scale, so the efficiency is quite bad in that region. And that are for a number of reasons. I won't go through them in detail now, but we will just make sure or see that here is a gap, and if we really need better light sources in that wavelength range. And our ask is basically to say that we would like to have enough light in that wavelength range. And with enough, we mean 1 to 10 to a bit more, 10 plus milliwatts, depending on exactly what we would like to do. We would like to have a reliable source, a narrowband source that we can really measure fluorescence. It should be able to couple into an optical fiber. And there is an issue with light below 300 nanometer because that's can be absorbed by DNA and can be mutagenic. So this is really what we are interested in getting. And these are the type of devices that you're working on to try to meet that ask. But what if we go to medical imaging in general first to really motivate, why are we interested in this? So then, I mean, we have a number of techniques that we are using today in hospitals. And one of them would be computed tomography, CT. And that's basically X-rays that you send from here, detect from here, you rotate it around the body so you get many different angles, and in that way you can get a tomographic image, and you see the tomographic images, and you slice basically the body by having the man or woman moving slightly between every rotation of the scan. So you're moving the patient through this tunnel here where you see this is rotating here. We also have magnetic resonance imaging, MRI. And that's basically RF techniques. So you're probing RF levels in an element, most likely in hydrogen. This is mostly what you're imaging in MRI. And you're trying to split energy levels, so nuclear magnetic or nuclear Zeeman effects. You're splitting that with a high magnetic field. So by having a high magnetic field, you're splitting some of its energy levels, and that's why you have the RF transition between those levels. So it's a very low energy. RF is very low energy, and you need to have a gradient in order to make an image. And if you have that, and you have these coils that can measure and send out the RF radiation, then you can get these type of images. Very, very nice. And you can also do functional MR, and that is basically looking at different elements than hydrogen. And you can also see the bonding with hydrogen to different other molecules. So that's more what we call functional MRI. So these are both very, very conventional techniques and are used quite a bit. It takes some time to go through such an imaging modality, 5 to 30 minutes here. For X-rays, for computer tomography, you obviously have X-ray radiation, which is harmful. So you should be a little bit careful about that. But otherwise, they are very conventional techniques. But they are mainly looking, they are costly and have a big size and are very tricky to implement during surgery. So for surgical guidance, it's not good. But they don't, neither do they measure molecules in the tissue, but they rather measure hydrogen, which is in MRI, which is water, basically exists everywhere. And CT is just how you attenuate the CT radiation. So it's not molecular specific. So there is an option or a gap there that we could do better type of diagnostics. And light would be an alternative where we can do what we call optical biopsy. So basically measuring in situ, so on the spot when we are with the patient, measuring with optics and try to extract what type of molecules do we have in this type of tissue. And you have a number of those techniques that you can actually employ. Fluorescence would be one, Raman would be another, elastic scattering where we have also diffuse reflectance spectroscopy where you have scattering and absorption making an imprint would be a third alternative here. So these are things that we are interested in using for light. But we have one issue with light, and that's that it doesn't really penetrate very, very deep in tissue. So red light is the wavelength that penetrates deepest, and you can see how it's illuminating through my hand here. So you can actually see a few centimeters in tissue, but not much further. And that's a problem, a challenge that we are looking into, working with acousto-optics, combining light with with ultrasound waves to really see if we can probe deeper into tissue in that way. So typically, when you would like to look inside the body, I mean, typically light is only looking very superficially, so you can look at the skin, obviously. But if you would like to look inside the body, conventional technique to use is with endoscopes. So you go in with a fiber optic bundle, usually, where you have like 100,000 fibers in a coherent bundle. So when you make an image here, you produce an A on this side, it's actually coming out as an A on that side. So you can actually have an imaging guide in this way. So this is how conventionally endoscopes have been used for a long, long time. And you have that, so you have an imaging channel here, you have an open channel, but you can actually put in instruments, and you have an illumination channels here. And then you also have an airflow channel where you can make sure that you can make it clean just in front of the endoscope. So that's conventional endoscopy. Today we are mainly using cameras at the distal end of the endoscope. This is where we are interested in working right now at Tyndall to do that. But before we go into that, I would also like to see that, okay, we would like to use fiber optics typically to transmit the light and maybe also to collect the light if we don't have a camera or detector on that side. So that's typically how this is done. And we can do that in many different fashions. And we said fluorescence and diffuse reflectance would be two options. And we have spectra of those here. So this is diffuse reflectance. They are collected from colon tissue in patients at Mercy's Hospital. And these will be fluorescence spectra also measured in the same environment from different regions of tissue. And when we do this fitting here, we can actually try to extract what molecules are within that tissue. So that's really what we are interested in, to try to extract that type of information, to get molecular specific information to have better diagnostics. So let's take an example and let's take the colorectal cancer that I just mentioned from that study that we do at Mercy's Hospital. So this is a highly prevalent cancer. It's the second most common within men and third most common within women. And actually the survival rate is getting better, but it's far from good, I would say. So this is an area where we need to do better and treat those, manage those tumors better. One issue is that we detect them too late. So we don't really find them until they are too well developed and spread, and then they are more dangerous, obviously. So this is the reason. And one thing that we're doing now is to introduce a screening tool. So people, or I think everyone above 50 will now get in a screening program, or above 60, I don't really know. And it's different from different countries. So you will be asked to go for a screening for this, and this is why we hope to improve to get earlier diagnostics. And if you now see that you have, or believe that you may have a tumor, so the next issue would be to investigate that with an endoscope, as I just mentioned. And then you can go two different ways. You can have a colonoscope, and that goes through the colon, but you can also go through the sigmoideum by a different, smaller type of endoscope where you can go deeper into the body. And when you do that, you typically take a biopsy. That is a tissue sample that you send to histopathology analysis, and they will then say whether that tissue is normal or it's tumor tissue. And once that is done, and if you find that you may have a tumor there, then you go for further research investigations with X-ray, MRI, PETs, positron emitting tomography, or CT scans, as I mentioned. So these are standard techniques, conventional techniques used in the hospital that will then stratify the patient to see what type of treatment should you have. And then you make a treatment plan, and then you give one or several of these type of treatments: chemotherapy, radiotherapy, or surgery. And what we think we could actually make a difference is at this biopsy level, where we can actually guide where to take the biopsies. Because biopsy is not a non-invasive technique, it's an invasive technique where you take a tissue sample. So what we can do with an optical fiber probe is to see where you should take that to most likely find the tumor. But we can also make a difference at this stage. When you have started the treatment, we can see whether that lesion is responding to the treatment. For instance, if you have chemotherapy or radiation therapy, it's a good way to go in again and see, do they make any difference, especially for chemotherapy, because then you can tweak the cocktail of chemicals that you give the patient to be more, so that the patient will be more responsive. So this is an old image that actually came from Lund, where we do this type of endoscopy. So this is a coloscopy. So here we have the doctor, and here we have two of my students working with an instrument here to measure the fluorescence spectra that you see here What I actually are looking at is I put a fiber into this endoscope. The fiber goes out and investigate this type of polyps and see is this polyp dangerous or not dangerous. And so this type of patients can present hundreds of these polyps, and you can't take a biopsy from all of them because then you will certainly bleed a lot. So you will have side effects from that. So if we can go in and decide which places we should take a biopsy from, that would really be good. So, okay, so that was one example. So let's now talk a little bit about light-tissue interaction. So this is just a tissue slide that we see cross-section from the tissue. We send light in. It has different refractive index because it's not only air, but it's also water and lipids and other molecules in there. So it has a slightly higher refractive index. So you get the refraction at the surface. You get the spectral reflection at the surface. You also get diffuse reflectance, so that light scattering in tissue. The light is scattering every 100 nanometer approximately, so it's quite frequently. So that means that you are very, very frequent scattering. And you also have absorption, you have scattering effect, as I said. And that scattering can be elastic or inelastic. If it's inelastic, you can measure the Raman signal from that. But we can also have fluorescence. This is what we mainly will discuss today. So then it's interesting to see what type of molecules within the tissue will present fluorescence for us. And here we have just the spectra from in the UV range up into the visible. And this is the excitation spectrum. So the wavelength, how sensitive I are to be excited by different wavelengths. And you see different structures within the tissue. So NADH is a molecule that you have within the mitochondria. And so is the flavins. So they are responsible basically for the energy in the cells. You have a collagen and elastin. They would mainly be fiber tissue that keep tissue together. So extracellular structures. And you have lipopigmentation, so lipids basically, porphyrins, that's part of a heme cycle. You will have more nuclear stuff that also you could use to excite. So the ask that we have is to try to, or what we're trying to do in our research, is try to differentiate. So when we get some fluorescence spectra or reflectance, diffuse reflectance spectra, we're trying to extract these type of molecules and see whether we can measure the concentration of them. And if we then can say that, okay, we have a tissue with that combination of concentrations, that is more likely to be a tumor than normal tissue and vice versa. So this is really what we are looking for, to try to do spectroscopic analysis to try to extract whether this will be dangerous or non-dangerous, malignant or non-malignant in those cases. And this is just an illustration of an excitation emission matrix. So when you scan the excitation wavelength along this axis, you can see what emission wavelength you get on this axis. And here we actually have, again, colon tissue. So this is normal tissue, the A here, and this is tissue that is malignant. So you see there is quite a difference in these maps. And what we are trying to do is to find out a way to miniaturize this so we don't need to measure everything here, because scanning this will take quite some time. But to get to discrete wavelengths and see, okay, if we measure at this wavelength here, there seems to be a huge difference between this peak and up here. So these are the things we try to use as a diagnostic tool. So when we do that, we actually have also other molecules within the tissue that's absorbing. So when we look for fluorophores, we have a competition with other molecules that are only absorbing but not really emitting any light, any fluorescence light. And they are also interesting because they actually do have two effects. One effect is that they limit the penetration, as we discussed before. So the penetration depth, you see the red light is going through the entire finger, the green light is only going through part of the finger. So the red light is in this wavelength region here somewhere. The green light is in this region, absorbing very much in hemoglobin here. The blue light or violet light is in this region here. It's even more heavily absorbed. And this fiber here has UV light, and then we see the fluorescence from the nail. We actually put across the fluorescent ink on the nail just to label that. So this is just illustrating how shallow the light is penetrating. And the shorter the wavelength, the less it's penetrating, basically. Not quite so, because you have some fluctuations here. And again, this is a log scale. But UV light typically doesn't penetrate more than 100 microns or so. So quite shallow. So that means that the probe volume is quite small. So if we send in light, and if everything is absorbed within 100 microns, this is the probe light volume that you can actually measure from, or you have some interaction with the light and can actually measure the signal coming out. So that means that UV light doesn't penetrate very far. Infrared light doesn't penetrate very far either, because water is heavily absorbing in the infrared range. But in the visible range, you have a little bit better transmission and near infrared range. And this is the transmission window of tissue where you can actually penetrate. Here, maybe 5 millimeter. In the visible range, maybe a millimeter or less. But here, a few hundred microns. And here, even less, 10 microns, basically, depending on the wavelength, obviously. So the other effect that I would like to mention here is that the absorbers not only limit the penetration and the probe volume of the light, but it also actually influences the shape of the spectrum, the emission spectrum that you look at. And that is because if you look at this, so you see the incident light coming out here, the light coming out has actually penetrated through the tissue some path. And if you look at this graph, you have quite some peaks in the absorption for some molecules. And this is again a log scale. You see that this will be per centimeter. So 10 to the minus 3, that means 10 microns that you will, what do I say now? 100 microns would be here somewhere. 10 to minus 4. 100 microns penetration of light. And that means that the light is not penetrating very much, but it's also influencing, because this is not a straight line, but it's actually quite peaked here. So that means that this dip here is most likely due to the absorption of the hemoglobin in the tissue. So this is a transmission. So this would be an absorption peak, transmission dip. So this is coming right at this place here. So that means that when we measure a fluorescence spectra here, we actually have an issue to see what is the concentration of the molecule, because it's not a linear relation between this intensity and the concentration, because it also depends on other molecules in the tissue. And that's why we usually would like to combine fluorescence with diffuse reflectors. So there would be other ways to measure the concentration of various molecules using fluorescence, and that would be the fluorescence lifetime. So we said that we can use the spectroscopic fingerprint, so to say, of every molecule to distinguish that from tissue fluorescence. So that we can do that in emission wavelength type of spectroscopy, but we can also do it in fluorescence lifetime. And the important thing with fluorescence lifetime, the good thing with that, is that it's typically measured at one wavelength. So that means that it will still be influenced by the absorbers, but it will always be attenuated the same. So the shape of this will not really depend on the environment, on the other molecules, the absorbing molecules. So measuring the lifetime here is actually independent of the surrounding molecules, while measuring the fluorescence emission spectrum will not be that. So this is something that is quite frequently used, especially in microscopy, where you do fluorescence imaging or imaging microscopy. So that's quite interesting. And here is just an example from our collaborators at UC Irvine, or UC Davis, sorry. So then again, by using a UV laser, a pulsed UV laser, sending pulse light here, and then by our collecting the emission through few different wavelength filters here, and by have different delays, by reach the same detector and amplifier, and then goes into this oscilloscope. And you can measure the fluorescence lifetime at 4 different wavelengths in this setup. We measured a fluorescence emission imaging system long time ago, as you see in the 90s. So that was based again on a pulsed light source, UV source. This was actually frequency doubled crystal laser that we sent in here, illuminated, took the image back, and here we have a camera unit with a few dichroic mirrors to get green and red, and actually we had 4 of them in this type of setup. And we also have a flip-in mirror to have the white light image. And then we tried to diagnose from the spectroscopic information what is tumor and what is normal tissue. So the tumor tissue has low intensity in this green range, G, and high intensity in this red range here, while the normal tissue have the opposite. And that's something that we demonstrated that on a skin lesion here. So this is basal cell carcinoma. You see the red region and the green region, and we plotted them with this function here. So red minus green divided by green, basically. And then we got the dimensional unit that we could illustrate, overlay on the image, on the white light image, to see where the lesion is. So this works actually perfectly fine. Now we're trying to do very similar thing, but now with a really smallest possible camera in the world. And this is within this IPIC project that we are running. So we have a platforms, and the platform we are talking about now is the biomedical platform, to have a world's smallest imaging system for guided surgery. And this will actually be used for many groups at Tyndall will be involved in this. So we are working with many people here. So MCCI, we have more your group to work on the light sources and on optical powering. We have packaging, we have communication, and we have biophotonics. So all of this is really of importance for that. And right now, what we're discussing is more illumination source and optical powering possibly, but mainly the illumination source, because we need UV light for that. And from the biophotonics side, we are working with a number of collaborators to really see where can we apply that. We are working, as you see, in bone surgery, in the heart, from different angles here, working in microscopy, working in breast cancer research, and in lung cancer diagnostics for bronchoscopes. But we also would like to build not only this miniaturized imaging sensor, but also miniaturized sensor for point measurement to do really guided surgery, just to say an optical biopsy guidance to say this is why we would like to do this. And this is just an early image that we have taken to illustrate the concept of that. So an example of that would be brain tumor resection. So we are working together with Cork University Hospital to see whether we can help the surgeon here So this is a neurosurgery suite. You have an optical fiber coming in here. You can actually point that to a tissue to help guide the surgeon what is diseased tissue and non-diseased tissue. And the system we have built so far is on a bench, basically, so it's not even micro optics, but it's really macro optics device that we have built. But it's working quite well, and we have studied that together with the people at CUH and come up with quite good results so far that we're just about to publish. But next step would actually be to miniaturize that. And again, we need good light sources for this. And this system is to combine fluorescence and diffuse reflectance to do the best possible diagnostic technique. And to be able to build it as a very, very small device that we could implement in surgical tools. So we could actually help the surgeon during surgery without this optical fiber coming out. And again, I will just remind you on what we are trying to do. We are measuring the fluorescence, we are measuring diffuse reflectance, and we are measuring them at the same time to try to compensate to be able to get the intrinsic fluorophore concentration, and that way do the best possible diagnostic. So that's basically what I would like to say about what we are working on in the Biophotonics team at Tyndall, saying that we are working with this micro camera and try to make that multifunctional, to combine it with reflectance, normal reflectance imaging, and fluorescence imaging. And for the fluorescence in particular, we need the UV excitation. We're also working with this micro sensor, and this is something that we are working in the MedFab project on as well, to really try to miniaturize to build a very compact sensor that we can bring into neurosurgery, for instance, or liver surgery that we are working together with the Cancer Institute in Amsterdam. But we're also looking a little bit wider than that. UV radiation is also very interesting by photonics for microscopy. And this type of microscopy is really surface excitation microscopy. So it's called USE. And this is a tool that I developed for histopathology, basically, to see whether they can make histopathology without any staining, to really be able to measure in vivo in the patient already without taking out the biopsy, putting it in formalin, and then stain it, and cut it, and do all of that. And that usually takes days. But if I just can take either the biopsy and measure it directly, or even measure in vivo, that would be fantastic. And again, by using ultraviolet radiation for that, as you see from the title. So typically 280 nanometer is a typical wavelength that they are employing to do that. And then by measuring fluorescence of various exogenous fluorophores, DAPI and rhodamine, but I can also measure in tissue autofluorescence, which is also something that I do quite a bit. And you can just enjoy these nice images here. So this is typically H&E staining. So this is what histopathology always is doing. And this is what it looks like in use. And this is again histopathology, H&E staining. And this is what it looks like in use. And this is actually hair and a hair follicle here. So this is what the hair looks like in H&E staining, and this is what it looks like in use. So with that, I would like actually to stop and saying that, okay, we have a need for compact UV sources in biophotonics, as I said, for imaging or for spectroscopy. Both type of devices is something that we are developing. I think we could take a strategic role here at Tyndall to try to develop those, and not only for those applications, but then look a bit wider to see what is the need in this area to really develop ultraviolet sources, a bit broader than the biophotonics applications that I have discussed so far. I mean, other applications would be water sterilization. There is a lot of sterilization now, especially with COVID. So this is really interesting. And then phototherapy as well. So for those things, again, you would like to use wavelengths in the range between, typically the UVC range, between 200 and 280 nanometer. That's why you do best sterilization and you have not producing ozone. If you go below 200 nanometer, then you start to produce ozone. And ozone per se is also killing virus and bacteria. So that's also one way to do the sterilization. But more health friendly would be to use the UVC range, where we can do this type of things. And as I said, it has become very, very important now with the COVID situation. So there is a lot of activities in that range right now. Phototherapy is something that you're treating skin lesions with quite frequently. So this is something that has been ongoing for a century, basically. So again, you need UV sources for that. So with that, I would like to thank you for listening to this, and I hope you should enjoy some of this at least. And I'm very open to take questions now, if you may have any.